In this video, we're going to refresh the two main types of chemical bonds that we have to have some familiarity with. We're going to briefly introduce them so that way when we go into naming compounds, you're able to quickly identify what type of compound it is, and then you can apply the rules for naming those to those types of compounds. So, we have two main types of bonds. We have ionic bonds and we have covalent bonds. We also have metallic bonding as well, but we're going to get into that later on in the year. So, when electrons are transferred, ions are formed and an ionic bond results. So, for example, sodium has 1 valence electron. Chlorine has 7 valence electrons. When sodium transfers its electron, it gives it up, it gives away. Right? So ionic bonding is all give and take. Sodium gives its electron to chlorine. Sodium becomes positively charged. We have an ion here. Chlorine gains an ion. Now it becomes chloride, has that negative charge. So now we have two ions that are of equal but opposite charges. These together are going to form a bond. And these bonds are just electrostatic forces of attraction. So because we have a positive charge here, we have a negative charge here, these are inherently going to be attracted together. In order to make a complete ionic bond, the level of charge has to be the same. So because I have 1 plus and 1 minus, this is going to work out just fine. But if, for example, I had 1 plus and 1 minus, then I have, or 2 minus, then I have to duplicate another plus charge to get that 2 minus to be balanced out. So it's basically a balance game. It's like if you're putting things on a balance and you have to keep adding things to both sides until they get equal. The other type is called a covalent bond, in which electrons are shared. Not transferred, but shared. So an example of this is oxygen and hydrogen when water forms. So oxygen inherently has 6 valence electrons. So you'll notice here that hydrogen has 1 and hydrogen has 1. So what we'll do is hydrogen will share an electron with oxygen, and oxygen will share an electron with hydrogen. And then the same thing happens over here. This one electron on hydrogen is going to be shared, and then one of these electrons is going to be shared. Because the goal is they want to have full octets. So as a result, oxygen has 4 valence electrons that are unshared, and then there's 2 shared here, which give us water. And if you guys remember from last year, this is where your Lewis dot structures come in. So you could have O single bonded to 2 hydrogens with some lone pairs here. So whenever you see these lines and dots like this, that's a dead giveaway you have a covalent bond. Now, when we look at these different bonds, we have a means that we can classify the compounds. So we can say we have ionic compounds. So like if you see NaCl or CaOH2, right? These are dead giveaways that I have an ionic compound. But if I have something like methane, CH4 or CO2 or H2O, then these are going to be molecular compounds or covalent. So oftentimes in class, you'll hear me refer to these as ionic compounds and molecular compounds. You got to make sure you distinguish them. Now, with ionic compounds, the main takeaway for this is you're going to have two things. You're going to have a metal combined with some sort of non-metal, okay? So your metal is always going to be first. That's the thing that readily loses electrons. It's going to be that cation. So typically the metal is going to have some sort of positive charge there. The nonmetals readily gain electrons. They become negative. They form those anions that we discussed previously. So your nonmetals are typically going to be negative. When a metal and a nonmetal react, a transfer of electrons usually takes place. I just showed you that in the last slide. Metals and nonmetals generally form ionic compounds. So that's how you can tell if you have an ionic compound. You want to look, what's the first element I have? Is it a metal or is it a nonmetal? If it's a metal, it's a dead giveaway to me that it's ionic. Yeah, or it could be a positive polyatomic, such as ammonium, which is kind of the rare exception because obviously N and 4H's are not metals. However, that does indicate when these are grouped together like this that you have an ionic compound. So a good example of this is ammonium chloride, NH4Cl. So we refer to them as ionic compounds. So some examples that I showed you earlier, you have Na plus and Cl minus. Again, this is a 1-to-1 ratio, so it's going to be NaCl. Perfect. Now calcium and chloride is a little bit different because calcium readily loses 2 electrons and chloride only picks up 1. So how do I make this balance? Well, I have a 2 plus here. I have a 1 minus here. I have to have another 1 minus to balance that out. So my formula should be CaCl2. Another common technique that people use is known as the crisscross method, where they bring the charge down here as a subscript, and they bring the 1 down here. The only tricky part about this is if you have something that's divisible by 2 or by 3 or something like that, where you can simplify the subscripts, you have to make sure you do that. So that's how we basically do it. You basically look and see what type of ions they form, and then match them up in a correct ratio that gives you 0. Now remember, on a test, they're not going to necessarily tell you that calcium's 2 plus and chloride's 1 minus. You have to predict that from their location on the periodic table. Sodium is in group 1, so that means to me that it's 1 plus. Chlorine is in group 17, which means it's a halogen. It's mostly 1 minus there. Same thing here. Calcium is an alkaline earth metal in group 2. So if it's in group 2, that typically indicates to me that they're going to have 2 plus charges. And again, chlorine, given that it's a halogen in group 17, it's going to be 1 minus because it just needs to gain 1 electron to have a full outer shell. So some properties of ionic compounds. Typically, they're solids with high melting points and high boiling points. Think about it this way. It takes a lot of energy for you to take salt, like table salt, to boil, right? To convert that solid to an actual gas. We've never seen that before. Sure, you've seen water boil and things like that, but never something like sodium chloride or sodium iodide like salt. Then also it takes a lot of heat to turn that from a solid to a liquid as well. When it's a solid, it's non-conductive, and it is conductive in what's called the molten form, aka you heat it up so much that it becomes a liquid. I also want to add to this, it's also conductive when it's aqueous. So what does that mean when it's aqueous? It's when the solid, the ionic compound here, is dissolved in water. So if I were to take salt and put it in water and pass an electrical current through it, it's going to conduct electricity really well. Now, formulas of ionic compounds. Again, these ionic compounds are electrically neutral. Their charges have to balance out. The formula of an ionic compound must have a ratio of ions such that the number of positive and negative charges are equal. These formulas are not molecular formulas, so that's really important. When you do ionic compounds, these are going to be in their simplest form, which is also referred to as an empirical formula. Oops, there we go. So if you have an ionic compound, it's going to be an empirical formula. Just keep that in mind. So let's look at this example here, Al3 plus O2 minus. So that's going to form Al2O3. Well, if they were to give you this and ask you for this, or if they were to give you this and ask you for this, you can kind of do the crisscross method, right? I can bring this 3, let me write it out here so you can see it better. And I have O2 minus. I can bring this 3 down here. I can bring that 2 down here, and I have Al2O3, right? And how do I know that works? 2 times 3 plus overall, this is going to give me a 6 plus. 3 times 2 minus overall is going to give me minus 6 or 6 minus. We'll make it that way. It looks better. So 6 plus and 6 minus, neutral. I know that's good. Okay. The other way I can do it too is you can actually draw out little squares to kind of help you out. Like if I have an Al3 plus and if I have an O2 minus, well, this doesn't work. Maybe I need another aluminum, which is Al3 plus, and then to balance that out, I need 2 more of these. Do you see how I have 2 aluminums? Aluminum, aluminum, and I have 3 oxygens there. O3. That's the other way you can figure it out too. So, in addition to this, you can also have them with polyatomic ions as well. But when you have polyatomics, you want to make sure you group them as one big thing. You don't want to split them up. So when we have phosphate, for example here, PO4 3-, we have to keep that P and those 4 O's together. We can't separate them out or split them up or anything like that. So we want to treat those polyatomics as discrete units, and when we have multiples of polyatomics, we have to use parentheses around them to denote that. So let's do an example with that crisscross method and show you what I mean. Here I have calcium 2+, and here I have phosphate, PO4 3-. Now, again, this is not going to balance because 2+ and 3- aren't the same. So here's how I can make this work. I can do it one at a time, or I can crisscross. Ca2 plus and Ca2 plus is 4 plus. 3 minus, that's not going to work. So maybe if I do another 2 plus, I have 6 plus now. 2 plus, 2 plus, and 2 plus. Overall gives me 6 plus. And then let's try it here. Well, 3 minus and another 3 minus. Okay, that's 6 minus overall. That's good. So this is balanced. So now I have to write out the formula. Well, I have 1, 2, 3 calciums. So it's Ca3. And I have 2 groups of phosphate. So if I were to do PO4 and then throw a 2 down here, that doesn't really look good, right? Because to a chemist, you would say, okay, I've got 3 calciums, 1 phosphorus, and then I have 42 oxygens. We know that's not right. I know in total I have 8 oxygens. So how do I represent that? Well, I have to use parentheses here to show that and say it's 2 groups of this PO4. Now, let's say you wanted to crisscross it, the quick and painless method here, PO4, 3 minus. Just bring the 2 down here, bring the 3 down here, Ca3, PO4, 2. Now keep in mind, this ain't going to work, right? Because I can't have 42, so I got to use parentheses, and then I get that there. Now you can also do the reverse of this too, right? I could bring this 2 up here, and I know that it's calcium 2 plus, and I could bring this 3, oops, not 3 plus, 3 minus up there, and okay, I know that's PO4, 3 minus. So you can also figure out with a compound what the charges are on individual things. So let's say you didn't memorize PO4, 3 minus as phosphate. You're just given Ca3, PO4, 2. You could figure out the charge on phosphate pretty quickly because we know that calciums in group 2 alkaline earth metals, those cations are always going to form a 2 plus. Alrighty, and the last thing we have to go through are molecular compounds, also known as covalent compounds. So again, when atoms share electrons, that's when we get our covalent bonds, or our molecular compounds, also referred to as covalent compounds. Again, these exist as discrete neutral molecules because they're sharing electrons. There's not an overarching amount of charge. If there is a charge there off of a covalent compound, that's when you get that unique polyatomic ion, because then that behaves as an ion when it bonds with other things. So when you have a molecular compound, here's how you can tell you have a molecular compound. You're going to have 2 or more nonmetals. So you're going to have a nonmetal first, and you're going to have a nonmetal first. Now I want you to notice that when nonmetals form ions, they're going to gain electrons, they're going to be negative. However, when we have a molecular compound or a covalent compound or a covalent bond, there's not going to really be these charges here because the transfer of electrons isn't happening. It's not that one thing's becoming negative and one thing's becoming positive. Rather, they're sharing electrons to achieve a more energetically neutral and less active state. So when we think about molecular compounds, you'll often see those as gases. So think of it this way. If you have CO2, how do you see CO2 in the world around you? This is a common molecular compound. We see it as a gas. In addition to that, some of your diatomic elements, which technically are molecules, you have N2, H2, O2, F2. These here are all going to be gases at room temperature. And if you think about it, their boiling points are going to be relatively low, and their melting points are going to be relatively low as well. Because keep in mind, if they often exist as gases, that means it's not going to be tough. It's not going to take a lot of energy for me to turn a liquid into a gas, and then especially not turn a solid into a liquid. So something to keep in mind. These are some common tests we can see here. So really quickly, how can you determine if a compound is molecular or ionic? Let's go through a few quick examples of that. Let's say I have FeCl3. Is this ionic or is this molecular? How can I tell? You want to look at the first element, and that'll give you a pretty good indicator. Is iron a metal or a nonmetal? Iron is a metal, so I know that this has to be ionic. Okay, so that's how you can determine it really quickly. Let's say I have something like C6H12O6. Okay, now this is weird, right? Because there's 3 elements. What's the first one here? Carbon is a nonmetal, right? It's to the right of that staircase. So this is a dead giveaway that this is molecular, or this is covalent in bonding and in nature. Okay. Let's do one more quick one. Let's say I have NaCH3COO. This is really long, right? It looks really complicated. Again, we're going to look at the first element. What is sodium? Is that a metal or a non-metal? Sodium's a metal, so this is a dead giveaway that this is ionic. Thank you.